Let's start with the second practice one because it specifically has one thing I want to make sure that we touch on. Pens, 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 pens. Sure. So this is practice number 2, Co-21A. Today is the 24th of February. We're looking at practice number 2 for midterm 2 for Lee. And we'll start at the very beginning with problem 1. I'm not going to write down so hopefully you've looked at the problem. I'll write down what's pertinent. Here's what the problem looks like. If you can see that. Ooh, can you see that? Do I need to turn off some lights? Okay. I'm always like, no. Oh yeah. Look, hey. That's much more visible. So the first problem says, find the values of A and B to make the following function differentiable everywhere. And what's not being said there, but certainly is heavily necessary, is that to be differentiable, we first have to make sure it's continuous. So that's the thing we're going to focus on first, is making sure that the A and B values give us continuity, and then whatever else we need to make sure that we get differentiability. So let's see. Our function is f of x equal to a minus b x plus b sine of x. And when x is greater than pi, ooh, fun, exciting. And x plus b cosine of x when x is less than or equal to pi. So really, the only thing we're actually concerned about here for continuity is making sure that the left-hand limit and the right-hand limit match. Because if those two things match, then the limit will exist. The function value will be that same value because one of the pieces already is that piece on that side. And so it'll be continuous as long as the left-hand limit and the right-hand limit match each other. I do think instead of just plugging in pi, like you could probably write this. I'm going to write one more step, but you could probably write we need a minus b times pi plus b times sine of pi. We need that to be equal to what you get when you plug in pi over here. Pi plus b times cosine of pi. Now, really, what I think you actually should be writing first is that the limit as x approaches pi from the left, using the piece we need to use, which is this bottom piece here, x plus, which I kind of got on the wrong side. Apologies for that. We need this left-hand limit to equal the limit as x approaches pi from the right of the right-hand piece, which is the top piece here, which I would never write that way, but I didn't write it, so you know. Yeah. To show the person who's grading your work that you know that for continuity, you need the left-hand limit and the right-hand limit to be the same. And then you achieve that by plugging in pi for the x's and setting them equal to each other and solving. So we'll pretend like I put pi on the other side and it's still right. It just looks weird. So let's see what we can simplify here. Sine of pi is 0. Cosine of pi is -1. So we have that a minus b times pi is equal to pi minus b. And there's not a lot more you could do here. I suppose you could isolate a, although I kind of feel like I'm getting ahead of myself and say that we need a to equal pi minus b plus b times pi. And that's all we can do at this stage, right? Because we have two unknowns and only one equation. The second thing we need to do is then work on differentiability. I would always start here though, because maybe starting here will actually give you like A equal to 1 or B equal to 0, or might give you a value for one of them that has to be the case. Not the case in this problem. So now let's look at differentiability. So looking at the derivative, or we're just going to look at the piecewise derivative. The derivative of A minus bx plus b sine of x is going to be negative b plus b times cosine of x. And the derivative of x plus b times cosine of x is going to be 1 minus b times sine of x. And we know the top part is when x is bigger than pi. The bottom part is when x is, I'm going to write less than pi, not less than or equal to, because technically we need the b value to be what it's supposed to be before we can say that they're actually going to be equal to each other. but you're probably fine just right there anyway. So then let's see. Just like last time, for the function to be differentiable here, we really need to make sure that the left-hand limit and the right-hand limit end up equaling each other. So the limit as x approaches pi from the left, and the left side is the bottom side, of 1 minus b sine of x. We need that to be equal to the limit as x approaches pi from the right of the bright piece, which is negative b plus b cosine of x. Notice you're not plugging in the pi yet, right? You're writing the limit of the function, and then in the next step, plugging in pi. So we plug in pi, sine of pi is still 0, so the left-hand side is 1. The right-hand side is negative b plus b times cosine of pi is also negative 1, so we get negative b minus b. So it looks like we get that 1 is equal to negative 2b, or b is equal to negative 1 half. And then plugging that back in up here for b, that's going to tell us that a is equal to pi minus negative 1 half minus 1 half times pi. I would probably take the additional step of simplifying this because pi minus 1 half pi is just 1 half pi. So we write this as a equal to 1 half pi plus 1 half. Or if you want to factor out the 1 half, you could have 1 half times pi plus 1. That's it. That's all they asked us to do. So again, important to make sure you read the question. Find all values of a and b that make the following function differentiable everywhere. Those are the only ones. B had to be negative 1 half. A had to equal pi minus b plus b times pi. So a had to be 1 half pi plus 1. Okay, it's not too terrible. I would also point out this kind of question appears on both practice exams. It's probably a good sign you're going to have one like that on your actual exam, right? I would think. Okay, unless you have questions, let's look at the next one. And feel free to stop me if you have questions. I'm really, really, really happy to say more or say less. Let's look at number 2 here. Number 2 is one of the ones I actually wanted to make sure I looked at. So given the following table of values, so given some values, which I'm not going to, I might write them all down. Yeah, let's write them all down. And the fact that G is invertible, evaluate the given derivatives. So we're asked to evaluate one, let's say A, the derivative of f of x times g of x at x equal to 2. And B, we're asked to evaluate the derivative of g inverse of 2x evaluated at x equal to 2. And we're given the following, that we're given that f of 2 is 3, f of 3 is 1, g of 2 is 4, g of 4 is 1, f prime of 2 is 6, f prime of 3 is 7, g prime of 2 is negative 1, and g prime of 4 is negative 2. Okay. So let's start with the first one first. They've asked us to find the derivative of f of x times g of x. So what do we need to do? The product rule. So here's what I'm going to write for A. I'm just going to do the derivative without plugging anything in yet. So I'm going to say that the derivative of f of x times g of x, I'm just going to spit out the rule. It's f prime of x times g of x plus f of x times g prime of x, or however you like to write it. And then I'm going to plug in 2. So I might write it this way. F of x times g of x prime evaluated at x equal to 2. I'm literally just going to plug in 2 for every x. So it's going to be f prime of 2 times g of 2 plus f of 2 times g prime of 2. I think it is worth writing this step. I don't think you want to jump straight to seeing what values you're going to plug in, because if you write the step, the person grading it's going to be like, cool, they know what they're supposed to do. Maybe they accidentally write down some incorrect values next, but this here I think is really like, oh yeah, they understand what's going on. Most of the partial credit. So then f prime of 2 is 6, g of 2 is 4, plus f of 2 is 3, g prime of 2 is negative 1. So we get 24 minus 3, which is 21. Not too terrible. The next one's a little harder, I think. So part B, we're asked to find the derivative of g inverse of 2 of x. Bless you. Yeah, the derivative of g inverse. So I want to find the derivative of g inverse of 2x. Okay. Add x equal to 2. Ugh, add x equal to 2. That's going to be interesting. So we know that's supposed to be 1 over g prime of what? G inverse of, yeah, I think your G inverse of 2x. That seems, I was going to say 4, but I think that, yeah. Still at the same value here, right? So we're trying to find, so this is still, right, evaluated at x equal to 2. So we're trying to find 1 over G prime of G inverse of 4. Okay, what's G inverse of 4? Show me on your fingers. You do have that many fingers. I see one person. Yeah, okay, 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 right. G inverse of 4 is 2 because G of 2 is equal to 4. So we're going to say this is 1 over G prime of 2, which is then equal to 1 over negative 1, which is negative 1. This problem is certainly designed to make you think about or actually remember the derivative rules, right? You have to actually know like the product rule as stated or the inverse derivative rule as stated. Yes. Oh, that's a really good point. I forgot about that. That's excellent. This is a really good question. I hadn't thought about that. So, right, if I'm doing, oh, yeah, right, because it's, yeah, 1 over g prime of g inverse 2x. Do I have to multiply the bottom by 2 here? Or the whole thing by 2? The whole thing, right? Because, right, yeah, because I don't love this. Yeah. Yeah, but no, you're totally right because you're doing essentially this part is your derivative of the outer part, and you have to multiply by a 2. Yeah. Wow. Extra, extra tricky here. So negative 2, not negative 1. Interesting. That seems, yeah. Yeah, that seems right though. Right, because if it was g inverse of f of x, you would do 1 over g prime of g inverse of f of x times f. Yeah. Yeah. Yeah, that's right. It's just weird. The reason I really wanted to see that one is because I definitely saw on your instructor's email that they said, right, they said like the things you have to know, right? They said topics include derivative definitions, derivative rules, derivative for inverse functions, implicit differentiation, related rates, and finding absolute extreme values. And on the other practice test, I didn't see any inverse stuff unless I just wasn't paying attention. I don't think I saw any. So that's why I wanted to look at that one specifically. But extra tricky there. Um, hmm. Yeah, let me think for just 1 second here. I know that might take a while. No, it's not going to be super helpful. No. Let's try and come up with another. Sure. No, sorry, it's all right. Sorry, I was trying to come up with another one, but like I don't. It's hard to make it up with these numbers here. Um, yeah. Let's go ahead and look at the next problem. 3. This one is find dy dx for the given equations. And one thing I'll point out is, oh, sorry, where'd my brain go? There was something I was going to say. Now I've completely forgotten it. Like it was right there, and now it felt really important too. Oh well. Well, it'll hopefully come back. So the first equation is x plus sine of xy equal to e to the y. What is this equation telling you you have to do without saying it in any words? Implicit, right? It's clearly an implicit problem, even though no one said implicit. So we got to use implicit. So differentiate both sides. 1 plus, let's see, the derivative sine of some stuff is cosine of the stuff. We multiply by the derivative of the inside part, which is going to require the product rule. It's going to be the derivative of x times y left alone plus x times the derivative of y equal to the derivative of e to the stuff is e to the stuff times the derivative of the stuff. This problem has an extra step in that you have to distribute this cosine of xy to this term and to that term before you can collect your y primes on both sides, on the same side. So we distribute, we get 1 plus. I would choose to write this not as cosine of xy times y, but as y times cosine of xy. I think it's a good idea to write things that you aren't taking the cosine of in front of the cosine or the sine or the natural log function. Over here, I'd write this as x times y prime times cosine of xy equal to e to the y times y prime. Let's bring that over there. So we have 1 plus y times cosine of xy equal to e to the y times y prime minus this xy prime times cosine of xy. And then if you're feeling lazy, you might just say on the right-hand side here, we factor out the y prime, we're left with an e to the y minus x cosine of xy. I wasn't feeling lazy, so I want to write the whole thing. And then finally, divide by e to the y minus x cosine of xy to get that y prime is equal to 1 plus y cosine of xy divided by e to the y minus x cosine of xy. Never pretty, almost ever with implicit. The same process every time. All right. Again, stop me or slow me down if you have questions about what we're doing. Otherwise, I'm just showing you how things work. I'm really happy to clarify anything. It's going to be y is equal to e to the negative x squared divided by 1 plus x cubed. I know what I was going to say. I'll point out that this question doesn't say anything about simplifying your answers, right? It says find dy dx for the given equations. It doesn't say not to simplify, but it also doesn't say to simplify. I would probably encourage you not to simplify unless for especially for like a bunch of derivatives, unless specifically told to simplify. If it doesn't say, I would say still don't simplify unless you've done everything else and you have time to kill. Then go back and simplify if you feel like that's something you're supposed to do. I'd probably ask first before I actually started simplifying if it didn't say one way or the other. All right, let's find our dy dx here. So here we have y explicitly as a function of x, so we just get to take the derivative. It's going to be quotient rule, bottom, times the derivative of the top. Okay, the derivative of the top is going to necessitate the chain rule. The derivative of e to the stuff is e to the stuff multiplied by the derivative of the stuff, which is negative 2x. So there's your bottom times the derivative of the top minus the top times the derivative of the bottom, which is 3x squared. We don't need parentheses around the 3x squared because it's only one term, essentially. Although you could write parentheses and it wouldn't be bad. You definitely need the parentheses around the 1 plus x cubed, though. They are required. And then the denominator squared. I still remember missing a point on one of my exams for not squaring the denominator, so make sure you square the denominator. Yeah. You could here. I don't think you need to here. Unlike the next question. So this one, I think this quotient rule is relatively simple enough that you don't need to use logarithmic. But that said, you totally could. I wouldn't, though. I feel like it's more effort than it's worth. Unlike the next one, where I do think the intent is for you to use logarithmic differentiation for the next one. So let's look at the horrors of the next one. Y is equal to, good God. It is x times x plus. I have to imagine she meant for there to be a parentheses there. Here's what was written. X plus 1 times x minus 2, but the 1 there is totally unnecessary if it's being multiplied. I really think they meant to have a parentheses there. That seems very, very, very likely to me. Otherwise, it's just kind of silly to write it that way. So I'm going to move forward with what I assume was the intent. It's an x plus 1 in parentheses times an x minus 2 divided by sine squared of x plus 1 in parentheses and then 2x plus 3 in parentheses. All that raised to the power of 1/3. Yes, this problem is screaming for logarithmic differentiation. Yeah, question.
All you have to do is like you could just distribute it.
Right, exactly. So if this was as intended, if this was really x times x plus 1 times x minus 2, like that, then really you could just say this is x times x plus x minus 2, which is x times 2x minus 2. Or really 2 times x minus 1. Either way. But again, I don't think that's what was intended. But you're right. If it was, you should then simplify it to make it easier. Okay, so logarithmic differentiation. So the first step is to take the natural log of both sides. I will again I'll point out, you could do this one without logarithmic. It'd probably be pretty terrible, moderately terrible. It's not, you don't want to do it that way. So the natural log of y equals, let's go ahead and do the first step of bringing down the 1/3. So it's going to be the natural log of all this to the 1/3 or 1/3 times the natural log of all of that. And here is a case where I think you really want to not show every little step because if you showed every step of breaking this apart, it'd probably be like 4 or 5 steps. Here's what we know. Here's what I've said. When you break apart a logarithm of a bunch of stuff multiplied or divided together, all the numerator stuff ends up with a positive log. All the denominator stuff ends up with a negative log. So this is going to break up as, let's rewrite it. You should write the whole equation. Natural log of y equals 1/3 times, and the 1/3 is going to multiply by everything. We're going to have the natural log of x plus the natural log of x plus 1 plus the natural log of x minus 2 minus the natural log of sine squared x plus 1 minus the natural log of 2x plus 3. I think that's a reasonable next step because every factor in the numerator has a plus natural log of that factor, plus natural log of that factor, plus natural log of that factor. Every factor in the denominator has a minus natural log of that factor, minus natural log of that factor. There aren't any powers we can bring down here, right? This squared does not get to come down there because it's not the power on the entire argument. So now we differentiate both sides. On the left, you always are going to get 1 over y times y prime, or dy dx, whichever way you want to write it. On the right, your 1/3 multiple sticks around, and you take the derivative of everything. So it's going to be 1 over x plus 1 over x plus 1 plus 1 over x minus 2 minus a little more complicated here, 1 over our stuff, sine squared x plus 1, multiplied by the derivative of our stuff. Okay, the derivative of sine squared plus 1, I should say sine squared x. The plus 1 doesn't matter, its derivative is 0. The derivative of sine squared, well, the derivative of something squared is 2 times your something to the first power times the derivative of your something. So the derivative of sine squared x is 2 times sine x times cosine x. Minus the derivative of the natural log of 2x plus 3, which is 1 over 2x plus 3, times the derivative of 2x plus 3, which is 2. And this is the part of the problem where you're like, I wish I was already done, right? Because really, right, you've already done all the work. The rest is just moving this y over here and replacing it with what it's equal to. So I would probably, unfortunately, feel like I have to write it. So I'm gonna say y prime is equal to, I'm not gonna write 2 more steps though. That seems insane. I'm gonna write y, which is gross, x times x plus, you know what I would probably do if I was short on time? I'd probably write the letter y and then draw an arrow pointing to it. But I'm gonna write it out. So it's x times x plus 1 times x minus 2, divided by sine squared x plus 1 times 2x plus 3 to the 1/3 power times all of this. 1/3 times 1 over x plus 1 over x plus 1 plus 1 over x minus 2. Don't get it. Don't try to simplify this part. No. Minus 2 sine x cosine x over sine squared x plus 1 minus 2 over 2x plus 3. And if you care that if you're worried about them like you could point out, hey, there's my y right there. I just replaced it with what it's equal to. Oof, it's still pretty gross, even using logarithmic differentiation there. There's something else I wanted to say here. No, I guess not. But so just be aware. Like it seems like in the other exam, there's also a candidate problem 4B that also seems like a candidate for logarithmic. So it seems pretty likely there's going to be something like this on your exam. All right, let's look at the next one. Again, just a reminder, you can stop me if you have questions. I'm trying to bring things in order here. All right. Number 3D. Now we have y equal to x to the 1/3 power plus the natural log of 1 plus e to the negative x. So to me, this looks like a pretty straightforward differential, or sorry, derivative. For x to the 1/3, we just get to use the power rule. It's going to be 1/3 times x to the 1/3 minus 1, which is negative 2/3. For this one here, we know from before the derivative of the natural log of something is 1 over the something times the derivative of something. And the derivative of 1 is 0. The derivative of e to the negative x is e to the negative x times the derivative of negative x, which is negative 1. You could probably convince me to simplify this and write it as 1/3 x to the negative 2/3 minus e to the negative x divided by 1 plus e to the negative x. But again, I don't really think that's super necessary. I'd probably leave it like this, unless I was compelled to do more. I probably wouldn't have written the 0 here, to be honest. Like, we know the derivative of 1 is 0. You don't usually write that, but it's fine. Ooh, let's do the next one. We have y equal to x times the arc sine of the square root of x. We should definitely think of the square root of x as x to the 1/2. So you can think of this as x times the arc sine of x to the 1/2 power. Or inverse sine, right? The same notation. I would hope I prefer arc sine as a notation just because it's easier to think of, but whatever. So our derivative definitely going to require the product rule because we have x times some other function of x. So using the product rule, in fact, you can even be more explicit here if you want. You can like label things. You can say, hey, I'm going to call this f. I'm going to call this g. My derivative is going to be my f prime times my g plus my f times my g prime. That helps. Nothing wrong with writing that out. That helps. So let's see. So f prime is 1. My g is just the arc sine of x to the 1/2. My f is x. My g prime is where things get a little dicey. So remember or recall that the derivative of the arc sine of just plain old x is 1 over the square root of 1 minus x squared. So the derivative of the arc sine of some stuff is going to be 1 over the square root of 1 minus my stuff, x to the 1/2 squared, times the derivative of the inside stuff, which is 1/2 times x to the negative 1/2. Of all of the problems you've seen so far, this is the one I would be most likely to think you might want to simplify. Like, I don't really want to, but if I was going to ask you to simplify any of these, this would be the one. And if I was going to simplify this, here's how it simplifies. So this first part's still just the arc sine of x to the 1/2. I feel like when I'm simplifying stuff, I usually like to go back to the square root notation. No good reason for that. It just is what I like to do. So I'd probably write this as the arc sine of the square root of x plus, let's see, I've got, well, first of all, the x times x to the negative 1/2 is going to be an x to the positive 1/2, which is the square root of x. So I've got a square root of x on top. On the bottom, I have a 2, and I have a square root of 1 minus x to the 1/2 square, which is just 1 minus x. Again, don't do this unless you're asked to. There's really no good can come of it, right? If you're not asked to simplify and you simplify, you're just increasing your chances of making a mistake. So really, really, really don't simplify unless you have to. I really like this. Cool. All right. So definitely you can expect to see product rule, quotient rule, power rule, chain rule, logarithmic differentiation, implicit differentiation. Those are all extremely likely to be on your exam. Like I would be surprised if any one of those didn't show up. All right, let's look at some of these wordier problems. Yeah, sure. Yeah. We'll look at all the we got loads of time. We probably yeah, okay. So here's problem 4. Suppose that the edge lengths x, y, z of a closed rectangular box are changing at the following rate. So first of all, I would draw a pic. Read that sentence before I do anything else. I'm going to draw the picture of the rectangular box, of a closed rectangular box. So I've got your usual kind of shape. I don't really know how long anything is. It doesn't really matter how long anything is at this point. I'm just trying to draw a picture to help me understand what's going on. And I'm going to call this x, this y, and this z, just because it feels pretty typical. And let's see, we're told that all of them are changing. We're told that dx dt is 1 meter per second. Dy dt is negative 2 meters per second. And dz dt is 1 meter per second. And then we're asked to find a few different rates of change. We're first asked to find the rate of change of the volume. Okay. So we're asked to find dV dt. And how this usually plays out is once you know what's changing and what you want to know how it's changing, you need an equation relating the non-time variables. It's typically just the geometry formula for the thing that you've been asked to figure out how it's changing. What's up, Bella? What do you need? Oh, I haven't even passed it around yet, but good call. Let's pass it around. So here it's just the volume of a box, which is not too terrible. It's x times y times z. And now to take the derivative of both sides, we're going to have to use the triple product rule. So on the left-hand side, we're going to get dv dt. On the right-hand side, it's always just one derivative multiplied by everything else not derivative. So we're going to get a dx dt times y times z plus a dy dt times x times z plus a dz dt times x times y. Not too bad. And then we plug in it, and they should have told us some other stuff. Let's see. Did they tell us some other stuff? Oh, okay, yeah, they did. So it said find the rate of change of the volume, and I forgot to see the last part here. When we know that x equals 4 meters, I'm assuming, y equals 3 meters, I'm assuming, z equals 2. So now we have all of the information we need to find what we're looking for. We want to know what dV dt is, and we know everything else. We know that dx dt is 1 meter per second, y and z are 3 and 2 respectively, dy dt is negative 2 meters per second, x and z are 4 and 2, and dz dt is 1 meter per second, and x and y are 4 and 3. So putting it all together, we get 1 times 3 times 2 is 6. Minus 2 times 4 times 2 is negative 16. 4 times 3 is 12. So we get 12 times 6 is 18. Minus 16 is 2. 2 what? Well, I think you could get away with not putting any units here since technically they didn't tell you the units for x, y, and z. But if you're supposed to assume that x, y, and z are in meters because their rates of change were in meters per second, then our units here should be meters per second times meters, which is meters cubed per second. which makes sense for a volume because it's some amount of volume per unit of time. Same idea for, so the next two questions are the same idea, just a different thing. So for part B, we're looking at the same stuff, just now it's for the rate of change of the surface area. Similarly unexciting in my opinion. But I guess we're not really looking for excitement when it comes to an exam, right? We're looking for straightforward, tell me what I want to hear. So why don't you all write the equation for the surface area? Why take a sip of water? Let's see here. Surface area should be this front face is x times z, and there's two of them because there's also a back face. This bottom face is x times y, and there's a top one because it is a closed box, not an open box. Be careful, they could give you the same problem where it's an open box, and then you only have one x times y instead of two x times y's. And then we have what else left? The side face y times z, and we've got two of those. And then same sort of deal. We're going to take the derivative of both sides. It's going to be a little bit messy. Our ds dt. Let's go ahead and factor out the two and just say, okay, the derivative of x times z is product rule dx dt times z plus dz dt times x. And then same deal over here. Oh, I should have, I meant to leave, I didn't mean to close my bracket just yet. Sorry. Plus, now for xy, same deal. It's dx dt times y plus dy dt times x. And for yz, same deal product rule. It's the derivative of y times z plus the derivative of z times y. Whew, just a lot of writing. Um, Something to be real about, like you want to practice writing this much, right? Like it is actually a not insignificant amount of writing. Your hands and arms can get tired, right? So definitely, just like you would train for anything, train for taking a test. Like obviously your test is tomorrow, so maybe not this one specifically, but in general, like make sure you are up to writing things down for a good 50-minute stretch, right? It is not a zero amount of effort task, aside from what your brain is doing as well. So practice how you want to play. Practice taking an exam. All right, so let's see here. So then we're gonna plug in all the things we know. So ds dt is going to equal 2 times. Let's see, we have our list of things here. Our dx dt is 1 meter per second. I wouldn't recommend writing in the units here. It's just a lot of writing units, which I don't think you need to do. Z was equal to, where'd you go? 2. dz dt is 1. X is equal to 4. dx dt is 1, y is equal to 3, dy dt is negative 2, x is equal to 4, dy dt is negative 2, z is equal to 2, dz dt is 1, and y is equal to 3. What a pain. 1, 2, 3, 4, 5, 6. Yep, that's the number of things I'm going to do. So I get 2 times 2 plus 4 plus 3 is 9. Minus 8, minus 4, plus 3. Let's see, that's a, don't tell me I'm going to get 0. That's disappointing. I don't know why it's disappointing to get 0. It just feels disappointing. So the rate of change is 0 square meters per second. Boo. It shouldn't matter, right? 0 is a perfectly fine answer. It just feels like you expected something to be changing here. Does that look right? I see a few like, did he do that right? Really? Right. When you get 0, it makes you question, did you do the problem right? Is I think is the problem with that. So let's double check just to be sure. 2 plus 4 plus 3 is 9, minus 8, minus 4 plus 3. Those numbers are right. Let's double check that these numbers are right up here. dx dt is 1, z is 2, dz dt is 1, x is 4, right? dx dt is 1, y is 3. Yeah, they're 4, 3, 2. I should just get on. dx dt, dy dt is negative 2, x is 4, dy dt is negative 2, z is 2, dz dt is what? Nope, those are all right numbers. So we get 0. Boo. Okay, let's look at the last one here. Diagonal length, which they do tell you, although if they didn't, you should still be able to figure it out. Diagonal length from one corner to another is just the square root of, and they like to call it lowercase s, square root of x squared plus y squared plus z squared. We know we're going to have to take some derivatives, so let's do ourselves a favor and rewrite it as x squared plus y squared plus z squared to a fractional power, 1/2. Just makes it easier for me to think about what I'm doing. So now, just like in the previous problems, we're going to take the derivative of both sides. So we're going to get ds dt equal to, all right, so chain rule, 1/2 times all of our stuff to the negative 1/2 power times the derivative of all the stuff. The derivative of x squared is what? That's part of it. Right, 2x times dx dt. And similarly, the derivative of y squared is 2y times dy dt. The derivative of z squared is 2z times dz dt. And then we plug in what we know. So we plug in, let's see, x, y, and z are 4, 3, and 2, respectively. So we get 1/2 times 4 squared plus 3 squared plus 2 squared to the negative 1/2 power times 2 times 4 times dx dt, which was 1, plus 2 times 3 times dy dt, which was negative 2, plus 2 times z, which was 2, times dz dt, which was positive 1. And I might just leave it like that if I was short on time. I recommend it. But if you had time at the end, we come back and be okay, 4 squared plus 3 squared plus 2 squared is 16 plus 9 plus 4, which is 29. So that's going to be 1 times 29 to the negative 1/2 power times, let's see, 8 minus 12. Oh, are you kidding me? 0 again? I guess simplifying it's worthwhile here. 0, what? Go ahead, yeah. Well, I don't think I think it's a coincidence that the answer ends up being the same here. I could be wrong, but right, because this inside part is a bit different than this inside part, right? This inside part, you're getting 6 things added together. This inside part, you're only getting 3 things added together. So they're not quite the same. I think it's really a coincidence that they both happen to be 0. So 0, what are my units here? Yeah, meters, not just meters per second. Right? It's a rate of change. It's got to be typically some length, area, or volume per unit of time. I do think for questions like this, there is an expectation that at whatever you get even if I left my final answer like this, I would still tack on a meters per second here to get the units. Um, not skipping, but while we're on the subject of related rates, let's look at the other exam and do the other related rates problems. I think it's good to practice related rates. So this is practice number 1, number 5. So here's the problem. A light shines from the top of a 50-foot pole. Oh, yeah, this one's interesting. Oh no, this is not what I think it was. The ball is dropped from the same height, so 50 feet, from a point 30 feet away from the light. We'll talk about that specific thing in a second. away from the light. How fast is the shadow of the ball moving along the ground? 1/2 a second. Oh wow, they're really making this problem's got a lot going on. 1/2 a second after we drop it. And then they tell you that assume the ball falls a distance. So the ball falls a distance of s equal to 16 t squared feet in t seconds. Or its displacement is 16 times t squared. Okay, let's draw a picture. So we have a light shining from a pole over here, and the pole is 50 feet high. And they tell us the ball is dropped from the same height. So here's our ball. It's going to go that way. And now here, no, I guess it doesn't. Yeah, from a point 30 feet away from the light. So typically, and this is going to certainly be true here, we mean a horizontal distance when we say that. But it has to be, right? Because if we're dropping the light from the same height, it is 30 feet away from that light. So this distance here, even though it's not doesn't look to scale, that distance is 30 feet. And so then we're asking after 1/2 a second. So after 1/2 a second, how far will the ball have dropped? Well, if we plug in a half for t here, 1/2 squared is 1/4. 16 times 1/4 is 4. So the ball falls s of 1/2, which is equal to 4 feet. So right here, let's say that's going to be our 4 feet. And what we're asking is, how fast is the shadow moving? So first of all, just one question I'm curious about um, is the shadow going to be getting longer or shorter? Shorter. So just something to think about. So I would probably, although you can kind of go either way, I'm going to call this length here X. That's the length of the it's not really the length of the shadow actually, right? But it is how long the shadow is from here to here. So however much X changes by is however fast the shadow will be moving, essentially. Or I should say the tip of the shadow, really. So our job here is really to find dx dt. Hmm, interesting. This problem has I feel like this problem is feels almost like a extra credit kind of like this feels challenging. There's a lot of moving pieces, literally. A lot of moving pieces here to really think about. So let's see. Let's label other. So I'm going to label this height y because it's also changing. And I see some similar triangles. So I'm going to say that x over y is equal to x plus 30 over 50. Usually when you set something like this up, especially with these shadow problems, you can almost always rewrite the equation so that you have x's on one side and y's on the other side. The first step being typically to cross multiply. So I'm going to cross multiply. Ooh, this one's going to be a little bit more. I keep saying this. This is a harder problem than a typical shadow problem. So we cross multiply, we get 50x equal to xy plus 30y. I do not love an xy plus 30y. So let's go ahead and not distribute the y here like I did. Let's rewrite it as 50x equals x plus 30 times y. And let's just leave the y by itself and get 50x divided by x plus 30 equal to y. Yeah, yeah. Is that what I really want? Sure, you could do that. So, okay, question.
No, you can figure out like all the values for y, right?
I think so. Yeah.
Then would you just take the derivative of the one that's not?
Yeah, probably. I was gonna actually. I was. Yeah, you are right to say what you're saying. So I'm not thinking smartly about where I want to end up. I was about to do something different and solve for x because I was like, well, I know I want to find dxdt in the end, but even that's still going to give me a quotient. I'd rather not have a quotient. So I think your observation is excellent. I think staying here or here is probably the best way to go as far as having to differentiate both sides. But before we start differentiating both sides, I feel like we should try to identify what the things are. So let's see. We know that the ball has fallen 4 feet. So we know that this length here, so at the moment of interest, of course, we're going to write on paper here. So at the moment of interest, after, the ball has fallen for half a second, so time equals 1/2, our y value is going to end up equaling 50 minus 4, or 50 minus our 16 times 1/2 squared, right? Because the ball fell 4 feet. So the y value is going to be 46. Again, this is all preparing for after we take the derivative, plugging in the values we know. The other thing that's going to show up when we take the derivative of both sides here is dy dt. What's dy dt? They didn't tell us. Usually in a problem like this, often they'll say that something is falling at a constant rate. They didn't say that either. So this is also kind of a kinematics or object falling kind of problem where we have to actually use the derivative of the position function to find how fast the ball is going at the moment. So let's take a look here. In our equation, what's the height of the ball? Well, the height of the ball in general, the ball height at time t is y equal to 50 minus 16t squared. That's your ball height. Or in other words, it's like the ball falling due to gravity plus the initial height. And if there was an initial velocity, there'd be a term for that as well. But there isn't, right? We just dropped it. We didn't give it any initial downward or upward velocity. So then our dy dt, we actually get to find explicitly. It's not just given to us. So dy dt is going to be 0 minus 32t. Not surprising. That's your usual velocity at time t seconds after you dropped an object. Negative 32 feet per second per second. So then if we plug in 1/2, our dy dt at t equal to 1/2 is going to be negative 16. I'm going to use this problem. This is a good problem. I like this problem for how many things it's involving. I don't love it for a test because it's kind of a lot, but it's not totally unreasonable. Okay, so I think we have all the pieces we're going to need to plug in. Now let's go ahead and do the thing we probably normally would have done first, which is take the derivative of both sides. And I think probably, I don't know, I think either version is fine. Let's use the second version. So we've got 50x equal to x plus 30 times y. And now we're going to differentiate both sides. The derivative of 50x is going to be 50 times dx dt. For the right side, x plus 30 times y, we are going to have to use the product rule. So it's going to be the derivative of x times 30, which is dx dt plus 0 times the other thing left alone, plus, now we switch it up, we leave the x plus 30 alone and multiply it by dy dt. And now we're going to go ahead and plug in all the things we know. So we have 50 times dx dt equal to dx dt times y, but we know that y at the moment of interest is 46. So we have dx dt times 46 plus, let's see, x plus 30. Oh, do we know what x is? Oh, we don't know what x is, but we can find it because we know what y is. So we have to go over to this equation here or this equation here and plug in a known value of y to find a known value of x. Yeah. So bummer. thought I'd done all the work I needed to. So we have something plus 30 times dy dt, which we found to be negative 16. All right, so plugging in, we have 50 times x equals x plus 30 times our y value, which is 46. Gross. Okay, fine. So 50x equals 46x plus 30 times 46 is, let's see, 3 times 40 is 120 plus 3 times 16 is 1,838, so 1,380. So then we have 4x equals 1,380. X equals, let's see, that's almost 1,400. So it's 1,400 divided by 2 is 700, divided by 2 is 350, but we're off by 20 divided by 4 is 5. So we're at 345. Double check that. 345 times 2 is 690. Times 2 again is 12 plus 180. Yeah, that's 1380. These are kind of terrible numbers. So there's our 345. And now I think we've got enough information to finally solve for dx dt. So we're going to subtract this over here. Let's not multiply this out. Let's be smart. We're going to have 4 times dx dt equal to 345 plus 30, so 375 times negative 16. And since I saw that I have a 4 here and a 16 there, I'm just going to not multiply that and say dx dt is 375 times negative 4, which is negative 1,380 feet per second. Seems real fast. But it's negative, which we knew it should be because x is getting smaller. So if I was writing a final answer, I would say that what's the question asking here? The shadow is moving at a speed of 1,380 feet per second, which I will admit is concerningly large, but I don't think it's wrong. That question is hard. I feel like it could be made a little less hard by giving slightly nicer numbers, but it's hard to make the numbers on a question like this work out nicely. So I would say kudos to your teacher for coming up with an interesting problem, because it is an interesting problem, but it's a bit challenging. Any questions about this one at all, really? Yeah. Woof. Good question. Yeah. Hmm. So, what are my tips for staying organized on a problem like this? I don't know. Yeah. So I certainly, right. I mean, I drew my picture. I think the picture is vital for this problem. Like you could do it without it. It seems like it'd be real challenging to do without it. So I drew my picture, and the first thing I did, kind of atypically actually, usually when I'm drawing after a picture, I usually start talking about what's changing. So normally I would have said, okay, well, I'm trying to find how fast X is changing. And I should know or be able to figure out how fast y is changing. And that's what I did over here, right? I said, okay, yeah, dy dt is negative 16. That's again, it's a little different than our typical related rates problem, right? Often you're given one of the rates. You weren't given it here. So then, but I would say, right, writing down the things that I know is changing and the thing I'm trying to find is changing. And then after that, that's when I then would have started. And I kind of, as you notice, I like drawing lines to kind of separate things that I think are kind of different from each other. So I've got like my equation between X and Y over here. I definitely think you made the right call, right? We didn't want to go over here. Differentiating that on both sides, I think would have sucked. Um, if I had had my way about it without any input, I probably would have done this and said 50x minus xy equals 30y, factored out an x, and had 50 minus y equal to 30y, and then said x was equal to 50 minus, sorry, was equal to 30y divided by 50 minus y. I'm not saying that's better. I'm just saying that's probably where I would have ended up without thinking about it more fully. The reason I would have done this instead of this is because I know I'm trying to find dx dt at the end of the day. So having x isolated is a better choice than having y isolated. But honestly, this was the best choice. Avoiding using the quotient rule in a related rates problem is typically the best choice you can make, I think, if it's possible. Right? It's not always possible. And then after that, right, this is where I feel like all the work really happened. So we had our equation, we differentiated both sides, and then I was just, don't be afraid to write more. Right? I feel like oftentimes we are limited, certainly by the amount of space on an exam. Are you allowed to ask for scratch paper or use scratch paper or bring scratch paper? I don't know. I would say if you're finding like are your exams double-sided? So you can only use the back of the exam to write stuff down if you really need more space. But I would say, right, like I definitely wrote a lot of lines here and said, I took my derivative of both sides. I knew that my y value had to be 46 by, we found that already. But the x value was a bit of work over here. So we had to then take our equation relating x and y again and plug in. Yeah, it's gross. Don't love that. If I'd been, so again, if I'd been a little bit smarter about it, I could have avoided doing all this work. Because if I'd done this part first, and said, well, I don't know what x is exactly yet, but I know that I do know what y is. If I plug in y equal to 46, I see here that when I subtract these, I get a 4 times dx dt. Looking over here, no, that's not right. Nope, I'm saying something that is just kind of wrong. Yeah, kind of. No. I'm trying to justify like what I did, but no, it really doesn't come out as nicely as I'd like it to. I'm trying to pretend like it does, but it really doesn't. Ooh, yeah, and I definitely made a mistake here that I was talking too fast for anyone to catch. So I said something. I was like, oh yeah, our 345 times -4 is just negative 1380. But we don't have 345 times 4. We have 375 times 4, which is easier. It's going to be 1500. Be careful. I'd say as far as words of advice, I know I talk fast when I'm showing you things, but I'm trying to think slow. As someone else has said to me, go slow so you can go fast. Read the questions carefully, write things down carefully, make sure you're catching the signs. Yeah. I don't think so. I would probably write both things. I would write dxdt is negative 1500 because the x length certainly is getting shorter. But then the original question was, how fast is the shadow of the ball moving along the ground? You're not talking about any directionality here. So you're really just talking about the speed of the ball. We're talking about the speed of a thing as opposed to the velocity. We don't care. It's always assumed to be positive. You're saying, oh yeah, the speed is 1500 meters per second, regardless of whether it's going to the right or going to the left. Cool. All right, that's tough. Let's look at the last problem on this first one here, which should be much easier in my opinion. Find the absolute max and min of f of I want back on the second one, not the first one. Where'd you go? Sorry. Still the same type of lost the place completely. There we go. Min of f of x equal to x minus 3 x to the 2/3 on the interval from -1 to 1. What's our first step? We're going to find critical values. Specifically, we're going to find critical values in the interval. So if you end up getting like a critical value of 4, we don't care, right? The only critical values we care about are ones that are between -1 and 1 for this particular problem. All right, so we take our derivative. So f prime of x is going to be 1 minus 3 times 2/3 x to the -1/3. And either see where that's equal to 0 or see where it's undefined. All of you should be able to look at this right now and tell me for what value of x that derivative is undefined. It's undefined when x equals 0. Because 0 to a negative power is like division by 0. So we know for sure 0 is one of the critical points. And it is a genuine critical point because it's certainly in the domain of the original function. In fact, the original function is defined everywhere, but the derivative is not. It's probably a cusp at that point. Okay, but let's actually look at the whole thing now. If we simplify this a bit, we've got 1 minus 2 times x to the negative 1/3. Let's set that equal to 0 and solve for x. So I would probably do this as 1 equal to positive 2 times x to the negative 1/3, or really 1 equal to 2 divided by, excuse me, x to the 1/3, and then multiply both sides of x to the 1/3 to get x to the 1/3 equal to 2, or x equal to 2 cubed, x equal to 8. Right? X equal to 8. So yes, x equal to 8 is a critical value, and we don't care because it's not between negative 1 and 1. So not in the interval. It's definitely a thing teachers like to do, is give you a function where at least one of the critical values is not in the interval, so that they can see that you understand that you're not supposed to test that point. So ignore that completely. So what are we going to test? We're going to test the one critical point and all the endpoints. So f of 0, f of 1, f of negative 1. Cool. So plugging in 0, we get 0 minus 3 times 0, which is 0. Plugging in 1, we get 1 minus 3 times 1, which is negative 2. Reminder, 1 to any power is 1. But this negative 1 here, we have to be a little bit more careful. Plugging in negative 1, we get negative 1 minus 3 times negative 1 to the 2/3 power. Okay, negative 1 to the 2/3 power is positive 1. You can either do the squaring first and get 1, and then the cube root of 1 is 1, or the cube root of negative 1 is negative 1, but the negative 1 squared is still positive 1. So we get negative 1 minus 3, which is negative 4. So I would say that we have, let's see. So the absolute maximum, here's how I encourage you to write your answers to these questions. Write it as f of 0 equal to 0. If you write it that way, you're saying both you know where it occurs and what it is. That's not a good one to ask though. Let me ask. So the absolute minimum, I would say, is f of negative 1 equal to negative 4. So let me ask all of you. Is the minimum value negative 1 or negative 4? And it is, who votes for negative 4? I do. It's negative 4. It's not negative 1. So the negative 4 is the value. The negative 1 is the where it occurs. So the way I would read this is we have an absolute minimum of a value of negative 4 occurring at x equal to negative 1. The where is always the x, the what is always the y. All right, let's see. What else can I throw at you in these last 10 minutes here? Sure. Find, oh, I like this question too. The slope of the line tangent to the inverse of f of x equal to x to the fifth plus 1 cubed at the point 8 comma 1. Okay, so let me ask you all a question. I'm trying to find the derivative of the inverse function, right? Slope of the tangent line is just a code for derivative of the thing. So I'm trying to find the derivative of the inverse function. Okay, we know the what we probably do I know the formula for that? Maybe. Let's see. The derivative of the inverse function is, right, it's the 1 over the f prime of f inverse of x. I guess I'll write x. I don't love that. Sure, fine. Okay, so let me ask you, is 8 comma 1 the point on the function or the point on the inverse? Let's see here. If you plug in 8 here, do you get 1 out? Definitely not, right? This is showing me, oh yeah, we know that f of 1 is equal to 8. So f inverse of 8 is equal to 1. So here, we're really going to be plugging in x equal to 8. Right? Which makes sense, I guess, because they told us already. They told us we're finding the slope of the tangent line of the inverse function at this point on the function we're finding the slope of the tangent line to, which is the inverse function. So they're telling us the right thing. I just always have to think about how to wrap my head around it, to be honest. Like it's never clear to me like which thing is which, so I always have to think. So then this shouldn't be too terrible, probably. So we're gonna find f prime of x is 3 times x to the fifth plus 1 squared times 5x to the fourth. Now, if you look at this, which number seems like it's the more likely one you're going to have to plug in? 8 or 1? Assuming I don't hate you and don't want to make your lives terrible. The 1, right? Which it is, right? Because we're plugging in f inverse of 8. So now our derivative of f inverse evaluated at x equal to 8 is going to be 1 over our derivative here evaluated at f inverse of 8, which is 1, which is going to be 1 over, just plugging in 1 here, 3 times 1 to the fifth plus 1 squared times 5 times 1 to the fourth is 1 over 3 times 2 squared is 3 times 4 times 5, which is 1 over 60. Maybe it's probably part of this is probably my own personal bias. Like I personally find this challenging to think of the right way every time, which is maybe why I make more of it than it actually is. Just be careful with these ones. Make sure you're inputting the thing that you're supposed to be inputting, because to me it always feels kind of backwards. You had one other thing that was on my mind that, oh yeah, I know what it was. Where'd you go? So there we go. Yeah. This is from the first practice test she gave you, or the first practice, whatever you want to call it. Yeah. This is number one, problem 3. Find the equation of the line tangent to the graph sine of xy equal to sine of 2x plus sine of 3y at the point negative pi comma 0. So a couple things. First, find the equation of a line, not just the slope of the tangent line. So we know our equation is going to look something like this. Y minus 0 equal to your slope times x minus negative pi. Your only real job here is to find the slope of the tangent line. Obviously, this having x's and y's all mixed up together means we're going to have to use implicit differentiation. So let's go ahead and differentiate this implicitly. So we're going to get, let's see, the derivative sine of some stuff is cosine of your stuff. You have to multiply by the derivative of the stuff, which again is a product rule. It's 1 times y plus x times y prime equal to the derivative sine of 2x is cosine of 2x times 2. The derivative sine of 3y is cosine of 3y times the derivative of 3y, which is 3y prime. The thing I really wanted you to see with this implicit differentiation problem versus the other one we did is in this one, since you're being asked to find the slope of a tangent line at a particular point, plug in your point right after you differentiate both sides. There's no need to do any more algebra solving for y prime here. Just plug in negative pi for x and 0 for y. So doing that, let's see what we get. We get cosine of negative pi times 0 is 0 times 1 times 0 plus negative pi times y prime equal to cosine of 0. Oh, sorry, apologies. Cosine of negative 2 pi times 2 plus cosine of 3 times 0 is 0 times 3y prime. Okay, you definitely need to know cosine and sine of 0. Cosine of 0 is 1. Cosine of 0 is 1. Cosine of negative 2 pi is also 1. Right, because negative 2 pi is just one full revolution back to the starting place on the unit circle. So let's see what we've got. We've got negative pi times y prime equal to 1 times 2 plus 1 times 3 times y prime. So I would maybe subtract this over here. Yeah, it all feels kind of terrible. So you have negative pi y prime minus 3y prime equal to 2. Factor out the y prime. You get negative pi minus 3. So then you have the y prime, your slope is equal to 2 divided by negative pi minus 3. Or if you don't like the negatives in the denominator, you can multiply it by negative 1 over negative 1 and say it's negative 2 over pi plus 3. It feels better to me. And that is what we would then put in for our slope right there. So our equation would be y equal to negative 2 over pi plus 3 times x plus pi. But definitely, if you see an implicit problem where you're asked to find the slope at a particular point, whether or not you're finding the equation on the line, right after you take the derivative of both sides of your implicit equation, plug in your point and then solve for whatever y prime is left. All right, that is close enough to 2:30 that I'll have office hours over in El Centro as usual, and good luck on your exam tomorrow. I hope it goes well. Remember to get a good night's sleep, eat breakfast and lunch. Give yourself time to relax before your exam. Read the questions on your test carefully, slowly.